Hello everyone. In this session, we are going to discuss the concept of group, ring, and field. As we know, these are the basic concept of abstract algebra and widely used in the different domain. Like it is used in the security system, it is used to solve the different game theoretical problem, and also used in various machine learning models too. In this session, we'll talk about the basics of them, and I suggest you to explore their applications in these domain or in the domain as per your interest. So let us try to understand firstly that what exactly a group is. So when talking about a group is a algebraic structure. Now, what is a algebraic structure? First, we should understand that also. So when talking about algebraic structure, so suppose that if we do have some non-empty set, some non-empty set, let us consider them G, and we do have some operation with 8. So we call this operation as a binary operation if if when any two element or any pair of element of G operated with a star, the output should also be from G. That means what exactly? That if I take two element A and B from this non-empty set G and operate this A and B with the operation star, then output should also comes inside G. This property, or I can say this rule, make this operation as a binary operation, and a non-empty set along with a binary operation is called as a algebraic structure. Okay, so the first thing that we learn today is what, before directly jumping to the definition of group, that what is a binary operation and what is a algebraic structure. So this G is called as a algebra. This structure G comma star we call as a algebraic structure if this operation star is a binary operation. Okay, now this algebraic structure further classify into different categories that one is group, then we'll talk about semi group, then we do have some other structure like groupoid is there, then monoid is there. Okay, so these are the further bifurcation of this algebraic structure. Now, under what condition we'll say this algebraic structure forms a group, forms a semi-group, forms a monoid, forms a groupoid. Okay, so these are the some of the things related to these algebraic structure. Now, let us try to understand that under what condition we'll say this algebraic structure as a group or semi-group or monoid or groupoid. There are certain properties that we should know first before directly jumping to these algebraic structure. So the first property that we do have closure property, we call it as a closure property. An operation star is said to be closed or said to be satisfying the closure property if for every AB, if you are taking from this G set and operated then by the operation star, then output must be in A or G. If this condition satisfy, we'll say the operation star is closed with respect to group G, or in the reverse manner also G is closed with respect to operation star. It is quite similar with the binary property or binary operation, but there is a basic difference between these two. We'll just discuss that later on. The second property that we do have after the closure is known as associative property, is known as associative law or associative property. Now, what this property says, it may that most of you already aware about this property. What it says that if I take three elements and operate them like A star, B star, C, then in that case, their order does not matter. So that A star, B star, C can be written as A star, B star, C. That means it does not matter in what order we are operating this star, whether B and C operated first, then A, or A and B operated first and then C. If this condition hold, we'll say the operation star satisfy the associative law. Where what is ABC? These ABC comes from this structure G. The third property that we do have is called as existence of identity, is known as existence of identity, existence of identity. Now, what exactly it means? It means we are searching that whether the identity element exists or not for this operation star. Okay. Now, what exactly identity means? Let us try to understand. So, an element is called as an identity element. An element, we call it as identity element when it is operated to any of the element of the set G, that any element will be the output. Means we'll say that E, that should be in G, is the identity element, is the identity elements of this set G if A star E, or I can say E star A, because sometimes the operation need not be commutative. That's why over here, either it's operated from left side or right side, they should gives you the same output, which is the element itself, and if it hold, we called E as the identity element. Let me give an example to be more clear on this identity element. So suppose that in place of G, I am taking a set of positive integer. Let us take set of positive integer, and suppose the operation I am taking as addition. The usual addition that we already know, one of the elementary operation. So now when talking about plus in set of integer, positive integer, including 0, I can say set of positive integer including 0. Since I am writing positive integer, so over here I need to specify that I am making it as including 0 too. Okay, so let me correct it little bit, that what exactly this I or I plus is, so that it will be clear to everyone. So what I am taking it as set of integer, positive integer including 0. Okay, so we are not considering the integer on the negative side, even though that can also be considered. So what I'm doing, let I is the set of positive integer and plus is the operation. So I'm searching that with respect to plus, is identity element exists or not. So identity element is any element from this set of integer which when operated means added to any integer from set I, that integer comes out as output. And we know that if I suppose I take any element 4 from I, so what I need to add on this 4 so that I get it as 4. So yes, 0 is the element, and in addition, 0 is called as the identity element. So I can say for set of positive integer with the operation addition, identity element exists and it is 0. In the same manner, if I take the operation in plus of identity, let us take it as multiplication. In this scenario, suppose if I am taking set of natural number, natural number is starting from 1, not including 0. Natural number, and the operation is, let us say, multiplication, the usual multiplication. So what will be the identity element over here? Think on it. If get it, do let me know. So over here, identity, now we are supposed to find the element. Suppose if I am taking any element from n, let us say once again 4. So what need to be multiplied with 4 so that I get 4 as the output? And it's quite obvious that we know that 1, when multiplied to any number, that any number is the output over here. So either 4 into 1 we are doing or 1 into 4 we are doing. So we get the same integer 4 or that number 4. So I can say in multiplication, 1 is the identity element for natural number including operation. This identity, this operation multiplication. Suppose in set of natural number, I am taking operation as plus. So what is the identity element over here? What need to be added? If I take 4, so that I get it 4. Yes, it is 0, but in natural number, 0 is not here. So I will say identity element does not exist. Identity element not exist. Okay. So it depend on the set, what the set you are taking. It depend on the operation, what operation you are taking. An element is called as an identity element when it is operated to any element of the set, whether from the left side or right side. That element should comes as a output. Now moving ahead to the next property, the property number 4 is known as the existence of inverse. Is known as the existence of inverse. Let me rub the some part of this slide so that we can talk about the next property. So the next property is the existence of inverse. Let us try to understand what exactly we mean by inverse. So inverse means what? An element B is called as the inverse of A. An element B we called as the inverse of A. When they operated, we should get identity as the outcome. We should get identity as the outcome. Means what? Let me write it over here. Property number 4, and it's about the existence of inverse. So we can say B is called inverse of A. B is called as a inverse of A if when A and B are operated, yes, on any side, left or right, we should get identity element as the output. We should get as the identity element as output. So in this case, we called B as the inverse of A. When A is operated on B, we get identity as the output. When B is the inverse of A, then A is also called as the inverse of B. Okay, the last property that we do have is the property number 5 called as the commutative property, called as the commutative law or commutative property. Now, what it says that in your operation, the order of the element does not matter. That means whether I am operating A on B or B on A, we should get the same output. We should get the same output. Everywhere, wherever I have taken A, B, C, they are coming from your set G over here. These are the 5 basic properties that will help a lot to decide algebraic structure is group or not, or semi-group or not, monoid or not. Okay. Now, before talking about group, so let us talk about the existence of inverse. So the example that I have taken, which was what? Set of positive integer including 0 with the operation plus. So I'm interested to know what is the inverse, or is inverse exists in this set for every element. So suppose that I am taking an element as 4. So it is saying operate 4 to some other element and the output should be identity. In addition, we know that identity is 0. Okay, operation is plus over here. So 4 plus what gives you 0. Is there any element when added with 4 gives you 0 in the set of positive integer? Think on it. So there is no positive integer when added with 4 gives you output as 0. So what I should say, that inverse of 4 not exist. Inverse of 4 not exist in positive integer with the operation plus. Positive integer with the operation plus. On the same side, if in place of positive integer, I take the set of all integer. I take the set of all integer with the operation addition Then in this case, what will happen? Let us try to understand. So now what should be added in 4 so that I get identity as 0? So in positive integer, I am having minus 4 also. In integer, positive, negative, both side is there. So I do have minus 4 also. So when 4 is added with minus 4, we'll get it as 0. So I can say inverse of 4 is minus of 4 for set of integer with the operation addition. Okay, so this is how we can understand. This is how we can understand these 5 property. Just a minute, man. Now, on the basis of which one satisfied by algebraic structure, the naming is also given. The naming is also given. So, if a structure only satisfy the first property, we called as a quasi group. We called it as a quasi group. Quasi group, or sometime it is called as a groupoid. Okay, so only first property, that is the closure property satisfy, we called it as a quasi group or groupoid. If a structure is satisfying first two property, if a structure is satisfying first two property, that means it is closure as well as associative, we call that structure as semi-group. We call that structure as semi-group. In the same manner, if it is satisfied the first three property, if the first three properties satisfy, then in that case, that structure is called as monoid. That structure is called as monoid. If a structure satisfies first four property, means first, second, third, and fourth. If all the first to fourth properties satisfy, then that structure is called as a group. So if someone is asking to check whether an algebraic structure is a group or not, we are supposed to check it whether it is closed or not. Closed means it is satisfying closure property or not. We'll check about whether associative law is hold or not, whether identity element exists or not, whether inverse exists or not. When talking about inverse exists, for every element of the given structure, the inverse must exist. For every element of the given structure, the inverse must exist. There is one more extension of a group called as a abelian group. If all the property from first to this fifth are satisfied, then such structure we called as a abelian group. Okay, so this is what the conceptual summary of the things related to a group. So if someone is asking to check a structure is semi-group or not, just check the first two property, which is closure as well as associative. If someone is asking to check whether an algebraic structure is group or not, we are supposed to check the first four property. Okay, to be more clear, let us take one example on it, and it will help you a lot to understand that how exactly we'll check that a structure is a group or not. So let me write an example. So suppose that we do have a structure, and over there G is having element as 1, minus 1, I and minus I, the image, the iota, and the operation is given as multiplication, and the operation that is given as multiplication. Multiplication, the usual multiplication. Okay, now we are supposed to check the algebraic structure G with the operation this multiplication is a group or not. Is a group or not. This is what the problem we are supposed to think on. Okay, so now we are supposed to check the first four property, and on that basis we'll decide this structure is a group or not. Now, the first property is closure property. So, for closure property, we are supposed to check what? When two elements of this G is operated with each other, the output should also be from G. Okay. Now, we do have four element, and we are supposed to make many pairs are there. In 4 out of 4, 4C2 kind of repetition, non-repetition is also allowed. So, for writing all the pairs, in place of writing all the pair, we can make a Cayley table. We can make a Cayley table, also called as a composition table. And a table will help you to list all the pair, as well as it also help you to decide or to check for the rest of the properties too. Let us try to write it. So on this side, I will put the operation, which is multiplication. This side, all the elements, and that side also the rest of the, or the all the element, better to say. And inside the entries, element after operation, when multiplication is operated. So first element, when 1 is operated with 1, so 1 into 1 is 1, 1 into minus 1, minus 1, 1 into I is I, 1 into minus I, minus I. Then the second row, minus 1 into 1, minus 1, minus 1 is plus 1, minus 1 into iota is minus iota, minus 1 into minus iota is plus iota. Operate iota on it. So iota into 1 is iota, iota into minus 1 is minus iota, iota into iota is I square, and we know that I square is minus 1. Then iota into iota is minus I square, so minus minus make it as plus 1, and the last entry is minus I, then plus I, minus I into I, so minus I square, that is plus 1, and this is plus I square, so minus 1. If you see, this Cayley table or composition table gives you all the ordered pair when operated to one another. And you can see every entry on this table comes from G. You can see in the table, we do have 1, minus 1 iota and minus iota. And they are there in the group G also. So no other elements. So it means what? When we operated two elements of this G, we did not get anything which is not in the structure G. So that's how we can check the closure property, and how to write it for closure property. We can simply write a statement from the above table, above Cayley table or composition table. We can see that for every A comma B, A star B, or over here the operation is not a star. So what the operation is dot A dot B belongs to G for every A comma B belongs to G. Hence the closure property satisfy. Hence closure property is satisfied. Okay, so this is how we check closure property by using the Cayley table. The second property is associativity. And as a default or trivial thing, we know that the multiplication is always associative. It does not matter in what order we are doing multiplication, it is always associative. So we can simply write that statement over here, that for every ABC from G, A dot B dot C is equals to A dot B dot C, and hence the operation multiplication is associative. The third one is about the existence of inverse. The third one is about the existence of identity. Before inverse, identity. And we know that by definition, that an element when operated to other, if that element comes out as the outcome, that element we call as the identity element. So just check the table. 1 is that element when operated to anyone. 1 operated to 1, 1 is the output. 1 operated to minus 1, minus 1 is the output. 1 operated to I is the output. 1 operated to minus I is the output. So you can see this 1 is the identity element, because when it is operated to any element, that any element is the output. So we can write that from composition table, we can say A star 1 or 1 star A, star means the multiplication here is A. That means the identity element for this operation is 1. And even we know that the multiplication, for the multiplication operation, the identity is 1, as we discussed in the previous example too. So yes, identity element exists, and if identity element exists, it is always unique. It's not like multiple identity element exist. Then moving to the fourth property, which is the existence of inverse. Existence of inverse. So in existence of inverse, what we are supposed to do in existence of inverse, we mean that A is called as an inverse of B. We call A as an inverse of B if when A is operated on B, when A is operated on B, the output should be identity. What is identity over here? 1. So simply in composition table, pay attention to the one outcome. Pay attention to the one outcome. So you can see 1 operated to 1, 1 is the output. So since 1 is star 1 is 1, so what can I say? Inverse of 1 is 1. Inverse of 1 is 1. What is the inverse of minus 1? So minus 1 operated on what? So that I will get 1 as the output. So minus 1 operated on minus 1, then we get it as 1. So that means minus 1 inverse is minus 1. We are supposed to check inverse for every element. What is the inverse of iota? Yes, think on it. What need to be multiplied with iota so that 1 is the output? So that 1 is the output. So you can see that minus I when operated to I, we get as 1 as the output. It can be observed from the composition table. So iota inverse is minus iota. In the same manner, minus iota inverse is iota. So you can see the G is having 4 elements and every element is having inverse. So now finally we can say that inverse for every element for this set G exists. Moving on to the last property, even though the task is done, the concluding remark from this table as well as this calculation, we can say the structure G and the operation star satisfying closure property, associative property, existence of identity, existence of inverse. Hence, the given structure is a group. Moreover, if we want to check the last property, which is about the commutative, what it says that A dot B and B dot A should be same. And as a result, that we know that multiplication is always commutative. A dot B is same as B dot A. So hence, we can further say, since all the 5 properties satisfy, so the given structure is a abelian group. The given structure is a abelian group. This is how you can understand this example. So when proving a structure is a group or not, it's quite important to draw this Cayley table or composition table, and it will give you clarity that which property is hold and which property not. Moreover, if there is any element whose inverse does not exist, we'll say for this element inverse not exist, and hence the given structure is not a group. I hope you understand this example. Let me write one more example for more clarity. So this time I am taking an example for a group G, for a set G, and G is having X type of element. The G is having X type of element such that let us put some restriction on this X. This X is somewhat from let us say 0 to, let us put the restriction 8, 0 to 8, such that the GCD of X and 8 is 1. This is how I have defined the group set G. Those X whose GCD with 8 is 1 will be the part of this G. Operation. Let us define the operation as multiplication modulo 8. This is how it is written. We call it as multiplication modulo 8. Okay, multiplication modulo 8 means what? How the operation is defined. So when I operated A on B with this operation, it is what? It gives you the remainder when A cross B divided by 8. Okay, try to remember this operation. Some extension of the basic elementary operation, which is plus, minus, multiplication and division, called as the multiplication modulo n. If it is n, remainder when A cross B divided by 8. One more operation is there which called as the addition modulo 8. addition modulo, let us say M. So how it is defined? A plus MB, it gives you the remainder when A plus B divided by M. Divided by M. Okay. So quite similar of the congruence kind of relation called as a modulo relation. So come back to the problem. What it is given? G is having these property, the element is having these property, and the operation is multiplication modulo 8. So first, let us try to write the element inside G. So what will be the elements inside G? Those elements whose GCD with 8 is 1. So we know that it started with 1. And one more thing, these x comes from the set of integer. Huh? So it's not real number. They are talking about the integer. So we know that the GCD of 1 comma 1 is 1. So first element is 1. What is the GCD of 2 with 8? It's not 1, so we'll not take it. GCD of 3 with 8? Yes, it is 1. GCD of 4 with 8? It's not 1. 5 with 8? Yes, it is 1. 6 with 8? It's not 1. 7 with 8? Yes, it is 1. GCD of 8 comma 8 is not 1. So these are the element inside C, this G, and the operation is multiplication modulo 8. Okay, so now it comes out the same problem as the last one. Elements are given, operation is given. So the first thing is what? We are supposed to make a Cayley table. Cayley table or composition table. As already discussed for composition or Cayley table, operation is what? Multiplication modulo 8. So just put operation on the column. The element is 1, 3, 5, 7. 1, 3, 5, 7. What operation say? That multiply A to B, divide by 8 and write the remainder. So first column is 1 into 1, which is 1. 1 divided by 8, remainder is 1. 1 into 3, 3 divided by 8, remainder is 1. 1 into 5, 1 into 7, 3 into 1. Now 3 into 3 is 9. 9 divided by 8, the remainder is 1. 3 into 5 is 15. 15 divided by 8, the remainder is 7. 3 into 7 is 21. And 21 when divided by 8, the remainder is 5. 5 into 1, 5, 3, 15. 15 divided by 8, 7. 5, 5, 25. Divided by 8, the remainder is 1. 5, 7, 35. 35 divided by 8, the remainder is 3. 7 into 1, 7 into 3, 21. 21 divided by 5, 8, the remainder is 5. Then 7, 5, 35. 7, 7, 49 divided by 8, the remainder is 1. This is the Cayley table. Now you can see every entry of this table is from G. Either it is 1 or 3 or 5 or 7. So the first property satisfy. Hence we can say the closure property hold. You can write in the same manner as we did in the last problem. Property number 2 is for associative. As we know that the multiplication is associative and hence this multiplication modulo is also associative. The third property is about the identity. So what is the identity element over here? Which element when operated to any element gives output as that element, and you can see it is 1 over here. So identity element also exists in it. Property third done. Now property 4 is about the finding of inverse of every element. So what will be the inverse of 1? What is the output when 1 operated multiplication modulo 8 and it should gives you identity? You can see from the table it is 1. So inverse of 1 is 1 itself. What is the inverse of 3? Just see. So 3 operated to what give the output as 1? So you can see this column is 1. So 3 inverse is 3. Because 3 into 3 is 9. 9 operated on multiplication modulo 8. The remainder is 1. Inverse of 5. You can say the inverse of 5 is also 5. What is the inverse of 7? Inverse of 7 is also 7. Like just see, I just find out the identity element in this Cayley table for finding the inverse. And that pair is the inverse of each other. So now we did what? Closure is satisfied, associated is satisfied, identity exists, inverse exists, and for a group only these properties are needed. And hence, I can say the given structure, that is G with the operation multiplication modulo 8, is a group. Can I say it is abelian group? Think on it. So this is how you can understand a structure, whether a structure is group or not. I hope you understand it. Try to solve one problem which is about Zn, and the operation is given as multiplication modulo n. Okay, in place of Zn, let me write it as Z of 15. Now, what is Z of 15? Z of 15 is the same thing as decided over here. All those x whose GCD, all those x whose GCD with 15 is 1. Okay, so these are the structure in Z15. Operation, just make it as multiplication x 15 or multiplication modulo 15 and try to check it is a group or not. I hope you understand the concept of the group. In the next session, we'll talk about the things related to the ring and field. For now, let us close this session.